When you're working with 7-nanometer computer chips, you're playing at a scale where the tiniest manufacturing choices can have huge consequences for performance. And today, we're going to dig into exactly how that works. Yeah, it's kind of like setting up this incredibly complex chain of dominoes. A decision you make on a Tuesday can totally change how everything topples over on Thursday. It's a great reminder that it's not just what you build, but the exact sequence of how you build it that really counts. And that brings us to the core idea for today, what we call variability knobs. Now imagine these as tiny, seemingly minor process steps that engineers can literally turn to dial a transistor's performance up or down. And as you're about to see, twisting these little knobs can have some really powerful and sometimes totally unexpected results. Okay, so here's a crucial point. Not all transistors are created equal. You've got two main flavors, PMOS and NMOS. For what we're talking about today, just think of the PMOS transistor as the squeaky wheel. Why? Because it's super sensitive to this one specific type of force called longitudinal compressive stress. The NMOS, on the other hand, that's the workhorse. It's way more robust, its reaction is more complicated. And that makes our squeaky wheel, the PMOS, the perfect canary in the coal mine for figuring out what's really going on down at the nanoscale. All right, so let's jump into our first case study. This is a perfect example, and it all comes down to a critical step where timing is absolutely everything, the gate cut. So that begs a really fundamental question, right? In this whole intricate dance of making a chip, does it actually matter when you make that cut? Well, it turns out engineers have a few choices. They can do the gate cut early in the process, we call that gate cut first, or they can do it late or even last. And we're going to laser focus on that gate cut first option, because that specific timing, well, it leaves the whole structure uniquely vulnerable to stress. So why? Why is that gate cut first method so sensitive? It's basically a three-step problem. First, by cutting early, you've already structurally changed the area. Then you grow this high-stress material, silicon germanium, which you need for good PMOS performance. But, and here's the kicker, because that cut was already made, the whole structure is compromised. It can't handle that powerful stress properly, and so the stress basically leaks right into the transistor channel, and boom, performance takes a hit. Okay, next up, we're zooming in even further. This is a real game of nanometers. We're looking at a tiny structure called the Single Diffusion Break Trench, or SDB for short. And this is where it gets absolutely mind-boggling. If you make a tiny, tiny error while etching this trench, I'm talking about over-etching by just 4 nanometers, you get a catastrophic 15% performance drop in our sensitive PMOS transistors. 4 nanometers. That's literally just a handful of atoms wide. It's insane. So what's going on here? If you look at the PMOS transistor on the left, as that tiny overetch gets bigger, the longitudinal stress, that orange line, it shoots through the roof. It goes completely off the charts. But now look at our NMOS workhorse on the right. The same error, and it's barely a ripple. It just doesn't feel that stress in anything like the same way. For our final case study, believe it or not, we're going even smaller. We're talking angstroms now, tenths of a nanometer. We're going to look at a component called the gate spacer. All right, let's just get straight to the punchline on this one. What happens if the thickness of this little spacer varies by just plus or minus 10%? Well, for the PMOS, you get a massive 7% swing in its electrical current. And for the NMOS, it's less than 1%. I mean, that is just a huge difference in sensitivity. And here's the actual silicon data that proves it. Look at the performance of the PMOS, that's the green line. It changes dramatically with the slightest shift in that spacer thickness. And the NMOS, the blue line, almost perfectly flat. It barely notices. Once again, our squeaky wheel is screaming at us, telling us exactly what's going on. Okay, before we wrap things up, I want to show you one last thing. It's this fascinating and honestly kind of counterintuitive little quirk of physics, the temperature effect. We're all taught that heat is the enemy of electronics, right? Hotter is worse. But it turns out that's not always true. At higher operating temperatures, this thing called thermal scattering kicks in. Basically, all the atoms are vibrating so much that they create a kind of background noise. And that noise can actually drown out and reduce the chip's sensitivity to the stress variations we've been talking about this whole time. How cool is that? A totally unexpected effect. Okay, so let's pull back and look at the big picture. What does all this mean for the engineers who have to actually design and build these incredible chips? Well, this gets us to what we call the designer's dilemma. The main takeaway here is that we found 3 of these really critical variability knobs. Number 1, gate cut timing, where when you do it matters just as much as where you do it. Number 2, STB etch precision, where a tiny 4 nanometer mistake can absolutely wreck performance. And number 3, spacer thickness, where wobble of just a few atoms has a major impact. And the key thing to remember is these aren't just random one-off defects. No, they are predictable results from very specific choices in the manufacturing process. And that right there is why these knobs are so unbelievably important. They are critical levers in what the industry calls design technology co-optimization, or DTCO. What that really means is that the days of chip designers just throwing a design over the wall to the manufacturing team are over. They can't work in separate silos anymore. They have to work together in lockstep to figure out how to manage these incredibly sensitive little knobs. Which leaves us with one final pretty big question to think about. As we keep pushing the laws of physics right to the very edge, is it possible that the next huge breakthrough in computing won't come from some brilliant new design, but from the absolute total mastery of the manufacturing process itself?